Hi, everyone. Welcome back to another episode. In this episode, we will have Julius, who's a PhD student at the University of Oxford, and he's going to teach us all about high dimensional BO with random decomposition. Julius, we're very excited to have you with us. Please go ahead.
Yeah, thank you very much for having me. Right, so as you said, we are going to talk about high-dimensional BO, specifically about one solution to high-dimensional BO problem, where we want to utilize random decompositions to solve this problem. Right, so basically, what I will be talking about is basically the content of our recent, because last year's ICML publication, which was basically on the topic of utilizing random decompositions in high-dimensional BO. So just to give you a bit of a background, Bayesian optimization is a method for optimizing unknown black box functions by using a surrogate Gaussian process. So you can see an example of a fitted Gaussian process on this image. So Gaussian process basically provides us with a mean, which is shown with a solid line on the picture, and a variance, which is shown as a shaded region. So it basically fits the function to the known points, and on the points where we don't know the function value, it extrapolates the function from the known points and provides us with some uncertainty of that extrapolation. So based on such a model, we basically can select the next most promising point to query by optimizing so-called acquisition function. And a common choice for acquisition function is so-called upper confidence bound, or UCB for short, which balances exploration, exploitation, by basically selecting a point which has both high mean and high standard deviation, that is the square root of the variance, where the standard deviation is weighted by some exploration bonus B, which tells us how much we value exploration over exploitation. So this works great with small number of dimensions, but as we transition to high dimensional spaces, it starts to struggle. And one of the reasons for that is basically a well-known regret bound. So regret is basically the sum of the function values at the points we query and the optimal function value. And what was basically shown is that when Bayesian optimization style algorithm with the UCB acquisition function is run, the regret we obtain after T rounds scales as shown here. And this scaling basically is exponential in number of dimensions D. So this is not great. This is a pretty severe scaling. We can say that the curse of dimensionality is touching also the Bayesian optimization. So there's been a lot of different works trying to kind of like go around this issue. One family of methods was trust region methods, which basically restricted the search space to some region around the best point so far. And this basically is making the search much more efficient in high dimensional spaces, because basically, although the space is high dimensional, if we severely reduce the region over which we are searching for the next point to query, this basically means that the total space, even if it's high dimensional, it still has a relatively low volume. So it's still it's more efficient to search through it than through the entire domain. Another direction of research has been basically with this sparse method, with SASBO being one of the most popular methods, which basically fits the Gaussian process with a special prior that then effectively turns certain dimensions off. And surprisingly, in practice, many dimensions can simply be turned off without any loss of the optimization process. Basically also making the optimization process much easier, because we basically kind of like effectively reduce the dimensionality of the problem to a much smaller one. Another work was the projection methods, which basically devised some projection scheme that allowed the algorithm to conduct the optimization in a much lower dimensional space, and then project it to the original space by this projection, by this mapping. And another also flavor of this method is the latent space BO, where this mapping was a neural network that was trained usually in an unsupervised manner on a much bigger unsupervised data set. And finally, the last one, the last direction of this research, which I'm going to focus mostly in this presentation, is the additive methods, which basically assume that the function can be written as a sum of some subfunctions, with each taking arguments of much smaller dimensionality than the original than the full function, basically.
Julius,
so,
is it?
Yeah.
If you go back, please, one slide. So, is it fair to say that all these high-dimensional BO methods have been trying to shrink the dimensionality in a way or another, and work in a lower?
Yes. Maybe this is not true for trust region methods, which are not necessarily shrinking dimensionality, but they are shrinking the space. So effectively, like the total volume is also like smaller of the space we are searching through. Right. So when it comes to the additive methods, if we assume that our function is additive, so it can be written as a sum of some smaller functions. Each of the functions we index by some fc, where c is some set of dimensions, and then the g basically is a collection of sets of dimensions, and this notation x square bracket c basically mean we only select the dimensions in X that appear in C. So for example, if our G is a collection of sets 1, 4, 2, and 3, then the black box function will decompose into a subfunction of dimensions 1 and 4, and then a subfunction of dimension 2 and subfunction of operating on dimension 3. And in such cases, we could model the function with a Gaussian process model, which utilizes a kernel function that admits the same decomposition. So we basically have an additive kernel function, which again is basically additive over those sets in G, and for each component, it only selects the dimensions appearing in that particular component. So if we exploit this fact, the regret bound literature that has been derived before basically allows us to basically express the regret bound in such a way that doesn't scale exponentially with the dimensions D, which is a huge improvement over just the standard Bayesian optimization. So furthermore, it was shown later on that usually it's sufficient to model the more real-world functions with simply a tree decomposition. So tree decomposition is a decomposition that only contains pairwise elements. So with each of those sets in the collection, there are only 2 dimensions at once. And if we were to draw a graph with an edge corresponding to each pairwise element in this graph, in this decomposition, sorry, there's an error on the slide, then we would not have any cycles. So for example, the graph we show on the left is a tree, doesn't have a cycle, and the graph on the right does have a cycle. So if we were to construct a decomposition where each node is a dimension and then each edge is a interaction term between those dimensions, then the graph on the left would correspond to basically what we call a tree decomposition, and the graph of the right would not.
Can I ask a question on the previous slide, Julius? So what does it imply intuitively for the real world function that it allows this tree-based decomposition? Can we say something on the intuitive level about that? Like what kind of property we should expect that kind of like gives this observation?
Right, I guess what we would so if 2 dimensions appear in the same component, that kind of means that changing both of them simultaneously will have a effect on the function which cannot be simply decomposed into like separate effects of both of them changing separately, right? So it's kind of like it's the effect that we will have on the function by changing those 2 dimensions is not merely a sum of the individual effects that changing each of the dimension has, but it's something beyond that. So it's something some basically effect which is a result of the joint change of those 2 variables. And I guess what we want to, if we only have 3 decomposition, that kind of means that we kind of assume that this will happen for at most 2 dimensions at once. So we will not have it for 3 dimensions, for example, if that makes sense.
Yeah, got you. Thank you.
Right. Okay, so the main problem with all of this is that if the function is truly black box, we have no idea how to know the true decomposition G, so the collection of sets. And we could learn, so the tree method mentioned before basically learns G by maximum likelihood by selecting such a G that produces model with highest marginal likelihood for the observed data. The problem is that this can be easily exploited, and we show a type problem where this maximum likelihood estimation can be exploited. So here we are showing a heat plot of a two-dimensional function, which is not additive, but locally appears as if it was additive. So locally appears as if it could be rewritten as a sum of two functions, fx1, fx2. And you can see that in the top right corner, there's a region where it's clearly not additive. That's clearly, there is some interaction between those two dimensions beyond just summation of those individual functions. And the state of our tree algorithm basically gets stuck in a suboptimal mode. That is the mode in the bottom left corner. So here we are basically showing with white crosses the initial design, so the initial points given to the algorithm. And then with red points, I'm showing the points that were queried by the tree algorithm afterwards. So because the tree algorithm believed in the full separation, it never really explored this top right mode. So never really found the optimal solution. So in general, in Bayesian optimization, we have very limited local data. And as such, it's not surprising that such a maximum likelihood estimator can just easily overfit. Thus, instead of relying on this limited local data, we basically considered using some data-independent predefined scheme for choosing the composition at each time step t. So such a scheme basically is some function, possibly randomized, that at each time step suggests some decomposition, and we fix this function before even the experiment starts. And what we basically show in the paper is that if you select a black box function, if you let an adversary select a black box function, more precisely, and this adversary might be trying to exploit your algorithm, and you also let this adversary choose the decomposition that the function follows, then after t rounds, if you run a Bayesian optimization algorithm with some fixed decomposition proposing scheme, which we denote ST, then with high probability, we obtain the following regret bound, shown below. And basically, this is a bit of an involved expression. I don't really want to dive too much into technical details, but there are two main quantities which govern how this bound scales, and that is this gamma t and epsilon t. They are both in red. And we will basically now discuss what exactly they mean. So if we were to assume that the true function decomposes as shown here, but let's say that we use a decomposition which is too simple. So for example, let's say that our scheme suggests us the decomposition which doesn't match the true decomposition, that it's too simple. In such case, the complexity is small. So this gamma t quantity in the bound will be small, but the mismatch expressed by epsilon t will be large. On the other hand, if we use a decomposition that is too complex, and we can see that, yes, here we definitely have too many additive components, and each of the components has basically too many arguments, much more than we actually need to model the function, then the mismatch is small. In this case, actually zero, because the true function is just, in this case, a special case of this complex function that we are proposing. But the complexity is large because we have many subfunctions and each of them operates on a large number of dimensions. As such, there is a trade-off between those two quantities. So there's a trade-off between gamma t and epsilon t. And we basically want to find some balance between them. So to keep gamma t small, we restrict ourselves to only the class of tree decompositions, which we defined before. And then this allows us to favorably bound gamma t. On the other hand, where we already do this restriction, so when we use tree decompositions, then we basically can make epsilon t small by using the following theorem. So this is another theorem we proved in the paper, which basically says that if the class of decompositions consists only of d-dimensional trees, then whatever the composition is chosen by adversary and whatever function is chosen by the adversary that follows as the composition, then for any data-independent scheme S that proposes the composition, this sum of the expected mismatches, so sum of the expected epsilons at each time step t, is at least as large as for the scheme which selects the composition uniformly at random. So it means basically that this expectation over the sum of mismatches epsilon t for any scheme S is at least as large as for the scheme SR, which basically represents the uniformly randomized scheme. So a scheme which basically just simply selects a decomposition from this class of all possible decompositions uniformly at random at each time step. So basically, the conclusion is that our algorithm should select 3 decompositions randomly, and it's perhaps surprising, but that is nonetheless the conclusion of the theoretical section of the paper. And based on that, we derived a practical algorithm, which we present here. So we call this RDUSIP, which stands for Random Decompositions UCB. And I will briefly go through how it works. So basically, we have the standard Bayesian optimization loop, where we fit a Gaussian process in line 5. And then in line 6, we optimize acquisition function to select the most promising point to query. And then line 7, we evaluate the black box function on the suggested point, and then add it to the data buffer. And then we basically repeat the loop. However, each time before we fit the Gaussian process in line 5, in line 4, we sample a random tree decomposition G. And then in line 5, when we fit the Gaussian process using a decomposition, which basically means that we use an appropriate kernel, which also follows the same decomposition, then basically that's what we do when we fit the Gaussian process. So we fit it with this, assuming that the function follows this random decomposition. And that is the main modification to the standard BO loop that we do in the algorithm. So basically, this decomposition is randomized as opposed to previous methods which try to learn this decomposition. And this decomposition is always a tree as well, as we discussed before. So after we designed this algorithm, we benchmarked it against other baselines, and we basically show the results here. So here, in the first plot, we are showing the comparison, the STIP-tank function, that stands for Stiblinsky-tank function, which is 250 dimensional. It's a synthetic function. In the middle, we have mixed integer programming tuning task, which is 74 dimensional. And then in the last plot, we have a 180 dimensional lasso bench problem, where basically the algorithm is supposed to tune the parameters for a weighted lasso model. So basically what we see here is that our algorithm, which we depict in orange, the orange curve usually is much lower than the blue curve, which basically corresponds to the tree algorithm that learns by maximum likelihood. And we are always lower than that, meaning we have lower regret. That means we basically find the points closer to optimum faster. So this was basically a tendency over basically most of the experiments we ran, that we severely outperform the tree algorithm. But we can also see that we also outperform other baselines, such as Hisbo in the purple curve. So this was very promising. And later on, we also did an ablation study where we showed how much of an improvement over the tree algorithm our algorithm brought when the dimensionality of the problem was changed. So we artificially changed the dimensionality of the Stiblinsky-tank problem and the lasso DNA problem, and we measured the improvement our algorithm brought over the tree algorithm. And what we basically observe is that the higher the dimensionality of the problem, the higher was the percentage of improvement in terms of the absolute regret over the regret achieved by the tree algorithm. And lastly, we also showed that this random decomposition feature has a plug-and-play nature. So we took a hyperparameter tuner called Hibo, which basically is a Bayesian optimization-based hyperparameter tuner, which has different components, such as multi-acquisition function, input warping, and also it uses an evolutionary algorithm to optimize the acquisition functions. And we kept all of them fixed, and we simply plugged the random decomposition component to it. So every time we fit a Gaussian process, we did it based on a randomized tree decomposition. And what we observe is that on the highest dimensional problems from the basemark suit, which are basically listed here, what we basically observe is that for every problem, RD Hibo, so Hibo with random decompositions, outperform the standard Hibo. So it provided a significant improvement over the baseline. Right, and these are the references I mentioned throughout. There is also a second page here, and yeah, I guess this is all for my presentation. So I will be happy to hear any potential questions you might have at this point.
Thank you. Yeah, thanks a lot, Julius. This was awesome. Thank you so much. Anyone has questions from the people attending?
Hi, Julius. Yes, thank you very much for your presentation. I was wondering if you had seen recent papers about BO in high dimensions saying that, for instance, vanilla BO are enough to cope with high D problems. There is a recent paper called Vanilla BO performs great in high D, and another one saying standard GP is all you need in high D for BO.
Yes, so I saw them. I saw both of them, and so yeah, I think they are very interesting. And so they both kind of seem to contradict each other in the sense that I think one of them is simply trying to say that vanilla-based optimization works great in standard in high-dimensional BO without any modifications, and the other one is saying that you need some specifically crafted prior. So this message seems to be kind of contradicting each other, at least to me. So I'm not entirely sure what to think of it at the moment. I think that it is interesting. Personally, I don't think it's possible that the standard Bayesian optimization without any modifications is able to perform well in high-dimensional problems, because we do have theory kind of saying that shouldn't be the case. However, if there is a specifically crafted prior, which is well suited for high-dimensional problems, then perhaps that would be possible. So I'm kind of leaning more towards believing in that paper, which actually has this special prior designed. However, so both of these papers are, I think, less than 2 weeks old, if I'm not mistaken. I probably assume that they've been submitted to ICML. At least probably one of them was submitted to ICML. So I would say we should probably wait for the review process to finish, see what the reviewers think of it, whether they get accepted or not. And also, I would really like to see for their code to be published, so that everyone can just test their code themselves. But yeah, I mean, in general, it's interesting. It's interesting to see something which potentially maybe will change the way in which we view high-dimensional problems in Bayesian optimization. But I think for now it's still very early stage, and I don't think none of these papers actually open source their code. So until this is done, I'm still kind of like I'm withholding my judgment on this topic. So yes.
Cool, yeah, thank you. By the way, how can people use RD UCB? Like, where is the code available?
Yeah, so the code is open source. So in the paper, there is a link. And we actually have two implementations. One is based on GPy, and that's the original implementation with which we run the experiment. And then there's the one based on GPytorch, which is integrated with the MCBO framework.
Cool.
Hey, Julius. Yeah, thanks for the talk. I had a question about, do you have intuition or examples where this method that you presented wouldn't work, and maybe why?
Well, I think a clear example of where our method would not work is if the function cannot be expressed as a tree, and it has basically interactions between the dimensions which are far beyond the pairwise interactions that the tree class assumes. So you could definitely create such a function synthetically, and yes, I guess that's in that case reducible algorithm will probably not perform that well. An algorithm which kind of can take those interactions into account, which will most likely perform much better. But I guess what was found out by the previous paper, the one proposed the tree algorithm, which I show here, that's the fourth paper here from top. Basically, usually the tree is enough to model real world functions. But I guess if you somehow found a function which cannot be modeled in this way, then I guess that would also be most likely a weak point for our algorithm. However, most of these high-D BO algorithm make some assumptions that you could potentially exploit, right? So, for example, SASBO is basically dropping some dimensions completely. So if all dimensions are useful and none of them are redundant, then some method like SASBO would also not perform well, right? So there's always some limitation, I guess, with those methods.
Yeah, okay. Oh, thanks.
Yeah, I would like to also ask a question, Julius. So could you go back, please, to the slide about RD-HIBO results? So, I mean, I find this very intriguing, right? That you could just add a random decomposition to an already existing algorithm and then kind of improve its performance, right? So have you actually tried to do that with like other algorithms, like Turbo, for instance, or Cosmo, if we're interested in doing like combinatorial spaces and so on? And what happened there? Did you see a similar trend of performance?
Yes. So in general, we tried to combine this with Turbo, and we saw that it can on some problems it can perform better than the both Turbo and RDUSIP alone. So it's kind of like we take best of the both worlds in a way. But I guess we are still working on the exact extension of this work, where we could kind of like perhaps make like publish as kind of like an actual algorithm which combines both of them and benchmark it more properly against other baselines. So I guess this is still in a way work in progress, but yes, from the early results we had, it kind of seems like that's something that you can do. So it seems like you could plug it to many more algorithms than just HIBO, and possibly you could in high dimensional spaces you can also obtain some improvement over just the vanilla version of that algorithm.
Got it. Okay. Yeah, I still have two questions, right, to ask actually. So unless there are more related questions to the topic itself, because these two questions are more general. So I want to ask you the following, right? So there seems to be, okay, today the hype is about large language models, right? Like we know that. And a lot of my friends who actually do BO are kind of depressed, because like they don't see necessarily a direct fit anymore between BO and large language models, right? So do you think there are any places in large language models where Bayesian optimization could still be useful actually? And if so, like any ideas what those could be?
Well, there have been a recent paper at AAAI, sorry, ASTAS, not AAAI, or actually, I think in the end it wasn't. Sorry, no, there was. I think it's still as a preprint. I think it hasn't been published yet. So basically, there was a paper which basically tried to model prompt tuning as a compositional Bayesian optimization problem. And basically what they showed is that they can deal with even with such high dimensional inputs as images or text. So yeah, basically they were able to tune the prompts for something like for image generation models, text to image generation models, as well as text to text generation models, just simple large language models basically. So yes, I think that basically you could probably easily utilize Bayesian optimization as some sort of a prompt tuner. Just the question is how to do it exactly is maybe a bit more difficult question, but in general, the problem setting itself matches very well this black box optimization setting. Another thing is that although like like whether we can use Bayesian optimization to improve large language models is one question, but I guess another question is whether kind of like Bayesian optimization maybe is filling the gaps that large language models cannot do, right? Because even one of the applications advertised of, I think, GPT-4 in the original technical report was that you can kind of use it for optimizing some, I think, molecules or something like that. So kind of trying to sell it as a black box optimization tool. However, in the current form, I don't really think this is possible on a large scale, just because large language model is simply trained with the maximum likelihood and it doesn't get the feedback back from the environment. So it in no way it's, I think, suited for exploring the environment and kind of like finding the optimum of some truly unknown new black box function. So in this sense, I think that yes, definitely, I don't think LLMs will in any way make Bayesian optimization redundant, at least not LLMs in the current form.
Okay, got it. Well, that was a big claim you made at the end, so let's see.
We will see.
And one last question, right? So we're asking everybody this, yeah. So there's a lot of complaints in the community about the review process, right? Like about how we get reviews and how we submit papers and so on. So what was your experience with that? And do you have any ideas to improve process of review that we go through?
Right. So I had both relatively positive experience and negative experience. I had very smooth review processes where like, yeah, the reviewers didn't have really any real issues, and like the only questions they had were kind of very relevant, and I could answer them relatively easy because yeah, I mean, they were like very relevant, and clearly the reviewers were knowledgeable of the field. However, I also had review processes where basically the reviewers had no idea what the paper is about and just blindly rejected it. I'm not entirely sure what the solution would be, because basically it's kind of like with getting a job, right? So whenever you are interviewing people, in general, the strategy is that you would always lean to reject, because the possible like bad possible disadvantages of hiring an unqualified person, the possible risk of that is much bigger than the disadvantages of rejecting a qualified candidate, because you usually find another pretty easily. So it's just that if you are applying for a job, you are at the beginning, your expectation is to be rejected, basically. So you kind of need to actively convince them not to reject you. And I kind of feel like with the review process, we cannot have the same thing, that we just have so many papers. And also we really want to make sure that what ends up in the main conference is of some relative quality, so that later on people who will be citing this work or trying to reproduce this work will not basically be wasting their time. So we don't want any false claims or results which are non-reproduceable or maybe sometimes even cheated. I wouldn't be surprised if those things happened as well with some of the submissions. So I think it's important that we have some review process that is kind of scrutinizes this and perhaps maybe sometimes a bit over rigorous with rejecting, but it's kind of a safety measure. But then what happens recently is that I think the machine learning conferences simply they reach their capacity. So there is just not enough reviewers. So what happens is that reviewers get assigned papers completely out of their domain. And usually they get assigned plenty of papers, like 10, 15 papers, which is just, it's impossible for an active researcher to spend that much time on reviewing. And if you think that they will be sitting for a month and reviewing paper for a conference that they get zero salary for and zero even any measurable benefits, then that's just not going to happen. So I don't know. It's just that maybe the field should kind of like rethink how we should scale now with the number of people interested, because it does seem like the number of active researchers in machine learning is growing, and it does seem like the field was not prepared for that, at least not in that scale.
But isn't it a GPU question then?
It kind of is. It kind of is a question of how to process the number of submissions in a relevant way. But I think the review process should stay. And even though it's frustrating, even though it takes sometimes you get rejected, even though you shouldn't. It's kind of some way of ensuring that in the end, what published it's actually of relatively decent quality and doesn't make any false claims. So I don't think we have a way of completely rejecting that.
I see. Sounds good. So yeah, with that, let's keep that as the last note. And Juliusz, I would like to thank you again for coming and giving us this awesome talk. So thank you, and I will see you in the next episode of Matti with a Researcher.